All right, we're back. In this video, I just want to make a short one to introduce you to a couple different things I've been working on. One is the Analog Discovery 2. It's a FPGA DAC and ADC board that can do all sorts of cool test and measurement. It's a little expensive, a little out of the budget range, but I got it back when it was cheap, and I got some university funding for it. So yeah, I've been testing it out, and we're going to show you how to do some work with its API. To write some C programs for it today. And so I guess a easy example to realize that would be I want to write a script to make some diode curves. So you guys have all seen a diode's IV curve, the current that it passes for a given voltage across it. And so we're going to test that today with a simple circuit. All we're going to do is put one of the Analog Discovery's voltage outputs in series with the diode and resistor, and what we need is the voltage across the diode and the current through this loop. And so the voltage across is easy. We're just going to say it's the voltage that we think we're supplying. We're going to tell the Analog Discovery to supply a certain amount of voltage, and we're going to subtract that from the measurement point between the diode and the resistor, and that'll be the voltage across the diode. And then to get the current, we'll take the voltage across the resistor, which is also at that measurement point, and of course the other side's the ground. So we have the voltage across it, and we know the resistance value because we can just measure that. So yeah, and then all we're going to do is switch out a couple different diodes, these two different guys, right here, and look at their curves. So of course you can go to any other tutorial and find out how to download the Waveforms software if you want to use the Analog Discovery with its pre-made software. Or you can also find out how to download the library for it has C and Python compatibility. When you download it, you get this whole folder with a bunch of examples. I would recommend just looking through that because at least I find personally looking through a the SDK reference is kind of daunting, at least for me. And when you want to run your own, when you want to actually just compile and run one of these examples, you need to link it like this, and this will be in the maybe I'll throw this on GitHub or at least in the description. You of course need to have the G++ or GCC installed on your machine, and yeah, you just need to link it with this little guy right here. And then yeah, here's the program I'm running today. But yeah, then we're just running a loop from 0 to 5 volts. In increments of 1/10 of a volt, and we're going to take 32 samples per point and average them, and yeah, output that to a file. So let's see what some of these curves look like. Okay, so as expected, we have some nice diverging curves here for these two different diodes. This one here is the IN 4001, and this guy here is the Zener. But you can see here, yeah, we have a nice knee around between 0.6 and 0.7 volts. And then these guys turn on. Let's check it out for temperature now. We'll see how it varies with temperature. So after a super legit way of modifying the temperature, aka holding a soldering iron up to the diode at certain points on the iron, we have... Okay, so I initially thought this curve was moving to the left because of the temperature term in the Shockley diode equation, but it turns out that's not... I don't think that makes any sense because if you think about an exponential, as I change the exponent, it just changes the slope of that curve, right? It just changes the rate at which that curve is moving. So that's actually not what we see here. What we see is the same slope, or the same exponential time constant, if you will, or just constant. We see the same slope in these curves, but just that there's an overall shift. And so I think there's something else happening, so other temperature dependence, and it looks like a quick read, and this makes sense from my semiconductor classes. This is shifting because of by increasing the temperature, I'm actually increasing the Fermi level of the of one end of the junction. The electrons are holes at one end of the junction, and essentially decreasing the amount of energy that I need to put in to get current to flow through these guys, and it's also increasing the carrier concentration in the semiconductor. So I'm going to have to review this and probably make a better explanation. I guess there's a lot more to it than I thought so. But for now, this is still cool to look at. We at least validated the fact that we can take measurements and do some sort of controlled study with analog discovery. So I'm still happy, and that leaves more for next time. So that's a good thing. So anyway, thanks for watching, and I hope to see you next time.